Now let's move on to your magnifying power. So what is a magnifying power? Magnifying power is defined as the ratio of the angle subtended at the eye by the final virtual image to the angle subtended at the eye by the object when both, by both means the final virtual image and your object. Okay, so when both are at least distance of distinct vision. Okay, so consider your figure again. Now, in this case, the magnifying power will be defined as the ratio of the angle subtended by your final virtual image. This is your final virtual image. And if you see what angle it is subtending at this point or at your eye, it is making an angle of beta. Okay, subtend means to make an angle of beta or to represent the angle beta. Fine. So it represents your angle beta. Fine. So the ratio of the angle subtended by your final virtual image to the angle subtended by your object. Now consider your object AB. This object, let us suppose it is placed at a least distance of distinct vision from your normal human eye, and it makes an angle of how much? Alpha. So the ratio of this angle and this angle will be defined as your magnifying power. Now here, okay, look at this figure. Uh, we will need one more thing. Okay, suppose your object, this object AB, let us consider it as height h. This object AB forms a real inverted image A dash B dash. This image has a height h dash. This image will act as an object for your objective, and it will form a final virtual image of height h double dash, and the final virtual image is virtual and inverted. Fine. And the final image height is represented as h double dash. Fine. So now let's go back to your magnifying power. So here, the magnifying power can be written as the ratio of the angle subtended by your final virtual image. Okay, now if you go back in the figure, this final virtual image makes an angle beta. So the ratio of beta upon the angle subtended by the object. This is your object AB, and how much angle it is making? Alpha. So beta upon alpha. Fine. Now the condition is that this magnifying power, I can use this formula only when your object and your image both are at least distance of distinct vision. If you see here, my image form is at least distance of distinct vision, and I've considered another diagram in which I've placed my object at the least distance of distinct vision. Fine. From your normal human eye. Okay, now since your beta and alpha are small angles, your angle beta and alpha are small angles. If beta and alpha are small angles, then I can write tan of beta. Tan beta approximately equals to beta, and tan alpha approximately equals to tan of alpha. Fine. So let us substitute this condition here. Instead of beta, let us write down tan beta. Okay, give a approximately equals to sign, and write down tan beta, and instead of alpha I can write tan of alpha. Okay, now note I can write this condition only if alpha and your beta are very small angles. Okay, I'll just write down are small angles. Fine. Now if you go back to your figure, okay, now in this figure I want you to consider this red triangle. Fine. In this red triangle, your tan beta can be written as the ratio of the opposite side A dash B dash upon your adjacent side. The adjacent side is represented by UE. Fine. So instead of tan beta, I can write down the ratio of the opposite side H dash divided by your adjacent side UE. Fine. Where H dash denotes your image, A dash B dash height. Okay, it represents the or I can write image height A dash B dash. Okay, and the UE represents your object distance for eyepiece. Fine. In similar manner, your tan alpha can be written as, let's go back to your figure. For tan alpha, consider this blue triangle. So tan alpha is the ratio of the opposite side AB, which is denoted by H. This H represents the height of the object AB. Fine. So the ratio of the opposite side divided by your adjacent side. This adjacent side is denoted by capital D, which is your least distance of distinct vision. So I can write for tan alpha, this will be the ratio of the opposite side H upon your adjacent side capital D. Fine. So here H denotes the object height AB and D denotes the least distance of distinct vision. Fine. Now, on simplification, I can write this one as C, this UE. Okay, this will go to the denominator. So I can write this terms as H upon, sorry, H double dash, sorry, H dash upon UE, and this H, okay, this will be multiplied with the denominator. So H, and this capital D will go to the numerator. Capital D. Fine, fine. I can simplify it further. Okay, so if I simplify it further, I can write down this one as H dash upon H and D upon UE. Fine, fine. Now, if you remember, I've okay. Let's revise one concept. Okay, so in our linear magnification, okay, in your lesson number 13, I've already discussed about this linear magnification. Now, in your linear magnification, this linear magnification M, okay, this magnification M equals to h2, the height of the image, by h1, the height of the object, which in turn can also be written as V, image distance, by U, which is your object distance. Okay, so we will use this concept, fine, for your convex lens, the concept of linear magnification. Fine, fine. So using the concept of linear magnification, consider for your objective. Okay, for objective, I can write the magnification M as the ratio of the image, sorry, the ratio of the image height h dash upon the object height h. Fine. Okay, so this term h dash upon h will denote the magnifying power for your objective. So let me write this one, equals to magnifying power of the objective. Fine. Where what is MO? MO is the magnifying power of objective, and your MO equals to the ratio of the height of the image h dash upon the ratio of the height of the object h, which in turn can also be written as the image distance VO by the image distance UO. Fine. This is your magnifying power of the objective. Now, in similar manner, the magnifying power for the eyepiece. Okay, so let us consider the magnifying power of the eyepiece. ME equals to, or ME denotes, first let me write down, ME denotes the magnifying power of eyepiece. Okay, this magnifying power ME should also be equal to the ratio of the height of the image h double dash upon the ratio height of the object, which in turn should be equal to its object distance and your image distance. Okay, but first let us discuss about, or first let us discuss this one, h double dash by h. So going back, now in this case, for your eyepiece, the magnification can be written as the ratio of the height of the image h double dash upon the ratio of the height of the object h dash, which I have written here, h double dash upon h dash, which in turn can be written as the ratio of the object distance capital D upon the ratio of the ratio of the image distance. Okay, this is image, the image distance, this a double dash b dash is the image formed by your eyepiece. Okay, so this is the image distance, capital D is the image distance. So the magnifying power m is the ratio of the image distance upon your object distance ue. Fine, so I can write down the magnifying power equals to the ratio of the object distance upon the image distance ue. Fine. So d upon ue equals to the magnifying power of the eyepiece, which is represented by me. Okay. So your total magnifying power m equals to mo upon me. Fine. Now, uh, if you remember the linear combination of the lens, okay, let's go back to your linear combination of lens. Okay, so in your linear combination of lens, your lesson number 16, okay, in lesson number 16 we have discussed if there are more than one lens, okay, if there are more than one lens, then the total magnification will be the product of your the magnification produced by your lens 1, the magnification produced by the lens 2. We can verify the same concept in your compound microscope. So the total magnification produced by this two lens should be the magnification produced by the objective and the magnification produced by the eyepiece, which I have written here. The total magnification m equals to the magnification power of the objective and the magnifying power of the eyepiece. Fine. So let me put this in a box. Fine. So this is the total magnification produced. Fine. So that's it for today's class. Thank you. Okay. And if you have any confusion for the compound microscope, okay, but for the compound microscope, when the final image is formed at least distance of distinct vision, you can ask me. Okay. Please don't hesitate to ask. I will re-explain it to you again.